This is the Masking Handbook for Audiometry. In this video, we'll be looking at why masking at a level that's 10 dB below the level of the test ear signal cannot result in overmasking. Here are our minimum possible interaural attenuation values as taken from the various studies that have looked at IA. We know these are extreme values, the least attenuation that is known to occur for the various devices at the various frequencies. We use these values to make decisions during audiometry and masking for all our test subjects. But we also know that most of our subjects actually have higher attenuation characteristics than what we see here. In 1974, Frederick Martin made an interesting observation on how audiometric results can provide information on a situational-based interaural attenuation. Robert Turner recognized this and proposed that we can sometimes observe values that are closer to an individual IA rather than depending on the min-IA values that are population-based. He pointed out that the degree of an air-bone gap cannot exceed the IA of a given situation. Put another way, he claimed that the IA of a given situation cannot be less than an observed air-bone gap. Let's take a look at this idea. Here we have a mild conductive hearing loss in the right ear. The masked bone conduction thresholds are all at 0 or 5 dB. Here are the min-IA values for the various frequencies superimposed on the air-bone gaps. We see that the gaps are all less than the min-IA values. Here is a moderately severe hearing loss, and we have air conduction thresholds shown on the right ear. We see the min-IA values superimposed on the air-bone gaps. Turner's observation is that the IA in this situation must be greater than the min-IA values that we keep in mind as reference for attenuation. If the true IA values in this situation were the actual min-IA ones, then the right ear air conduction signals would have entered the bone tissues of the head at these min-IA levels, and the subject would have been able to hear them there. Instead, the signals remained with the right ear at least up to the point of the unmasked air conduction responses. Let's look at 1000 Hz. Here is a fuller picture of attenuation for TDH phones. At 1000 Hz, the min-IA value found from the various studies was 40 dB. But if we notice, the mean or medium values for 1000 Hz using TDH phones tends to be around 60 dB. The max values found are like 75, 85, or 80. So the max values tend to be around 80 dB. So the range of attenuation using TDH phones is probably going to be somewhere between 40 and 80 dB, with the average being around 60. Here is a severe hearing loss in the right ear with unmasked air and bone thresholds being shown on the right side. We know the min-IA values, and this situation does exceed those at all frequencies. If we know that the person did not have the typical min-IA values, well, what can we say about the interaural attenuation here? At 1000 Hz, we have an 80 dB air-bone gap. We can't say for sure that this unmasked air conduction threshold is accurate because the value exceeds what we know the minimum attenuation to be. We also don't know which ear this unmasked bone conduction threshold is coming from because it too is unmasked. However, although everything so far is unmasked, we can observe something about a situational interaural attenuation. As Turner stated, the IA cannot be less than an air-bone gap. We can say that for this subject at this frequency in this situation using TDH phones, the IA must be at least 80 dB. So we're claiming a situational interaural attenuation. We can use this knowledge to our advantage when thinking about masking. In this case, we'd definitely want to mask both the air and bone conduction results coming from the right side. Would need to do that. So we'd be masking our non-test ear, which is the left ear. We've established or claimed a SIT IA value of 80 dB for this frequency, this person, and this earphone. What would happen then if we delivered 80 dB of narrowband masking noise to the left ear? The theory behind the optimized method is that it would be a safe level. The SIT IA value means that this level of narrowband noise would remain with the left ear and not cross cross to the right ear, where it could cause overmasking. In other words, the masking noise crossover value to the test ear right side would be 0 dB. There'd be no active masking effect on that right side. The optimized method recommends that the initial masking level be 10 dB below the air conduction threshold of the test ear. With this approach, the IML is guaranteed to be a safe level, even if it's a very high level of noise, such as 70 dB. The SIT-IA value allows us to recognize that it's safe. A criticism might be, since the 1000 Hz bone conduction threshold of 0 dB is unmasked, then 80 dB might not be the actual attenuation value. If you mask the bone conduction on the right ear and it showed up as 35 dB, would that make a SIT-IA value of 45 dB? And if it was 45 dB, then 70 dB of masking noise would be too loud and cause overmasking. The answer is no. 80 dB is still the situational attenuation value. If the unmasked bone conduction threshold is coming from the right ear, we have a minimum value as to when the air conduction signal may have entered the bone tissues of the head, 80 dB. If the unmasked bone conduction threshold came from the left ear, we have an actual measure of attenuation here. The air conduction signal at 1000 Hz may have crossed to the left side at this level, but it did not cross below this level. So the SIT-IA must have been at least 80 dB. It doesn't matter where the unmasked bone conduction thresholds are coming from in this asymmetrical situation. We can use unmasked air and bone test estimates as a SIT-IA value that will be appropriate. Here we have a SIT-IA value of 80 dB because we can compare the air conduction thresholds of the right ear to the left ear. What about this situation, where the left ear has a sensory neural hearing loss? At 1000 Hz, for example, we no longer have an 80 dB SIT-IA value. We have a SIT-IA value of 45 dB. Does that mean we can't start with 70 dB of masking noise? The answer is we can still start with a 70 dB level, even if the SIT-IA situation is 45 dB. In a worst case scenario, it means that 25 dB of narrowband noise may cross to the right side. That's a lot of potential masking crossover. Let's take a look. If the bone conduction thresholds in the right ear are all 35 dB, then we have a true legitimate SIT-IA value of 45 dB. That means that 25 dB is at risk of crossing over. However, 25 dB of the masking noise from the left ear does cross. It is below the cochlear hearing of the right ear, so it will have no overmasking effect on the right test ear. What if bone conduction results are 5 dB in the right ear? Won't the 25 dB of crossover then overmask? The answer is no, because if the bone conduction result from the right ear was 5 dB, it would have a new SIT-IA value. Remember, the IA must be at least the same level as an air bone gap, unmasked or masked. With a new SIT-IA value of 75 dB, we have a potential crossover value of -5, and that means a 70 dB level of noise will be fully blocked to the left non-test ear side. In theory, during asymmetrical situations, a masking level that is as high as the air conduction threshold of the test ear will not result in overmasking. It doesn't matter what the bone conduction situation is. The better the bone conduction hearing, the higher the SIT-IA will be. The poorer the bone conduction threshold, the more that crossover of masking noise can happen without overmasking. As a safeguard, we start masking at a level that is 10 dB below the air conduction threshold. We're guaranteed not to overmask at this level. This is the Masking Handbook for Audiometry. If you liked this video, you'll love the handbook. For more resources on masking and to learn how to purchase the book, check out maskinghandbook.com.